Hello and welcome to ICND2 Lab 4, Single Area and Multi-Area OSPF Configuration. If you're using the Cisco Press books, this video is best used along with ICND2's Chapter 9. This lab has 5 main objectives. The first objective shows you how to configure the OSPF network command to correctly match interfaces and put those interfaces in a particular area. Now to do that, the network command will use a wildcard mask concept, very much like access lists, to match particular interfaces. You'll also learn how to configure multi-area OSPF on an ABR by putting different interfaces in different areas. After that, you'll see how to distinguish between intra-area and inter-area OSPF routes by looking at the output of the show IP route command. And lastly, you'll see how a router picks its OSPF router ID. Lab 4 has 3 scenario steps. The first step begins with a working internetwork with OSPF already configured, in which we examine the working single area OSPF configuration on 3 different routers. In step 2, we'll add 2 routers to the mix and show how to configure a router to be the area border router and place the 2 new routers in 2 different areas. In the third step, we'll analyze the existing network to see how routers choose their OSPF router ID. Next, take a look at the already configured and working topology used in step 1 of this lab. R1, R2, and R3 have the IP addresses shown there. Now in each case we'll use a 255.255.255.0 subnet mask, so we'll end up with 4 subnets with a nice easy mask so we can stay focused on OSPF. For instance, in the subnet that all 3 routers are connected to, we have subnet 172.22.10. Off R1 we have subnet 11, off R2 we have subnet 12, and off R3 we have subnet 13. Additionally, note that all of these routers and all the subnets will be in area 0 for this step. The OSPF network command, like other routing protocols, lets the router match interfaces and then enable the routing protocol on those interfaces. However, the OSPF network command also tells the router which area to place each interface into. As a result, the OSPF network command provides a lot of flexibility, allowing the engineer to match a single interface, or just a subset of the interfaces, or all interfaces, and then place those interfaces into the particular area. Next, take a look at the OSPF network command syntax. The address and wildcard mask parameters work together, with the address being compared to interface addresses, but with the wildcard mask limiting that comparison. The next part of the video will explain a little bit more about how that wildcard mask concept works. Then, once an interface is matched with the network command, it's placed into the area listed there at the end of the command. Picking a good wildcard mask to use in the OSPF network command can be one of the most challenging things to configure in OSPF. The wildcard mask determines which parts of the address in the network command does the router need to compare to each interface IP address in order to match that interface. Now, wildcard masks are shown in dotted decimal format, so let's take a look at a couple of examples. First of all, a wildcard mask of all zeros tells the router it must compare all 4 octets of the address in the network command to each interface command. In other words, the interface IP address must exactly match the address in the network command. Now with the wildcard mask of 000255, it tells the router to only look at the first 3 octets of the address in the network command when comparing it to the interface IP addresses. So the 4th octet can essentially be ignored. With a wildcard of 0025.255, it tells the router to ignore the last 2 octets, only needing to compare the first 2 octets. For instance, if an IP address on an interface started with 1.1 and the network command's address started with 1.1, that network command would match that interface. Continuing on, a mask of 0.255.255.255 tells the router to only look at the first octet, and as you might guess at this point, a wildcard mask of all 255s tells the router not to bother comparing anything. This is the case of all interfaces will match this network command. Next, let's take a look at the command line interface on routers R1, R2, and R3. You'll probably want to have your booklet open as it contains the initial config, and all 3 routers are already configured with OSPF in this case. First, let's take a look at router R1. If we do the show IP interface brief command, you see 1 line of output per interface. Notice the 2 fast Ethernet IP addresses listed there. Note also that there are 2 loopback interfaces with IP addresses configured. We'll look at those later when we talk about the router ID selection. Next, let's take a look at the OSPF configuration by using the show running config command. If we space down several paragraphs, we get to the router OSPF1 command. Now each router will have a router OSPF command with a number behind it, but the number is only important on a single router. For instance, router 3 is using OSPF process ID 2, where here is router 1 is using process ID 1, but they'll work just fine in order to exchange OSPF routes. Now if you look at the two network commands that are listed there, notice we've got network 172.22.10.1 with a wildcard mask of all zeros. That wildcard mask means exact match. So do we have any interfaces whose address is 172.22.10.1? Well, we actually do. So if you look up a little bit, you'll notice we see FA01 on the screen here, and there's its IP address. So that first network command would cause this router to match interface fast Ethernet 0/1, and as you see here with the area 0 parameter at the end, to put that interface into area 0. Similarly, on this next network command, we see 172.22.11.1 for the address with the same wildcard. That means we must exactly match the IP address shown there. And if you look further up, we see at FA00, conveniently on the screen here, we see IP address 172.22.11.1, an exact match. So again, because the area 0 parameter at the end of this network command, FA0/1 is also placed into area 0. Next, let's move over to router R2. Now in R2's case, if we do a show running config command, and if we page down to where we see the OSPF configuration, there we have it. It shows router OSPF1 happens to be the same process number, and a single network command. Notice the wildcard mask in this case is 255.255.255.255, which means all interfaces match. So in router 2, this one network command matches all of router 2's interfaces, no matter what their IP addresses are, and places all of those in area 0. Next, if we take a look at router R3 and look at its running configuration with the show running config command, paging down a little bit to find that information. Notice here it has router OSPF2, a different OSPF process ID than router 1 and router 2, but it works just fine. And it's also got a single network command. Now in this case, it's got a wildcard mask of 0.0.255.255, which tells router 3, just look at the first two octets of your interface addresses and see if they start with 172.22. Well, as it turns out, we can see toward the top of the page that both FA00 with an address of 172.22.13.3 and FA01 with an address of 172.22.10.3 indeed have the same first two octets as the network command. So in this case, router 3 will put both FA00 and FA01 into area 0 because of the network command. Now let's go back to router R1 and take a look at the routing table. If we do a show IP route command that you see here, notice we have a couple of routes that have an O in the left-hand column. Now if you look toward the top of the page, we see that O, according to the legend, stands for OSPF. Now it turns out these O routes, the ones with an O in the left-hand side, are actually intra-area routes, routes learned inside the same area. Later we'll see that IA, as we also see here in the legend, means an OSPF route that's an inter-area route. Next, let's move on to step 2. In step 2, we've added 2 routers and 4 subnets to the picture. So as you see here in green, we have the same 4 original subnets that we had in step 1. Additionally, off router 5, we have these 2 additional subnets as well, subnet 172.22.115.0 and 172.22.15.0. Similarly, off router 6, we have a WAN subnet 116.0 and a LAN subnet 16.0. The expanded topology provides enough of a backdrop to discuss multi-area OSPF configuration. Frankly, the design shown here is a bit of overkill if this was all the network contained in real life, but it is useful for demonstrating the configuration. So in this case, the original 4 subnets are still in area 0, as you see there, but the 2 subnets off router 6 are going to be placed in area 6, and the 2 subnets off of router 5 are going to be placed in area 5. Now for this to work, router 1, which is now going to be connected to 3 different areas, needs to become an OSPF area border router. To do so, R1's S010 interface will be configured to be in area 5, and its serial 011 interface will need to be configured to be in area 6. For this lab step, all the new IP addresses on router 5, router 6, and router 1 have been pre-configured, and router 6 is already configured with its OSPF configuration. So we'll show how to add the configuration on both R1 and R5. So if we start at R1 and do a show IP interface brief command, and take a look at the new IP addresses, notice there we've got serial 011 and 010 with IP addresses that end in .115.1 and 116.1. Now if we get into config mode here on router 1, first we've got to get into OSPF configuration mode with the router OSPF1 command. Now notice the command prompt again changes, putting us in OSPF configuration mode. Now we need to add two network commands, one to match serial 010, inputted in area 5, and one to match interface serial 011, inputted in area 6. So to match the first interface, we'll do a network command with 172.22.115.1 with a wildcard mask of 0.0.0.0. That means exactly match this network command with an interface whose address ends in 115.1. So in that case, that happens to be the interface that's in area 5, so we'll put the area 5 command here, or parameters, at the end of the command, and there's the network command that will match the left-hand interface in the diagram. Similarly, we need to match the right-hand interface, serial 011, so we'll have a network 172.22.116.1 command with the same wildcard mask, meaning exactly match the IP address of interface serial 011. Now that one needs to go into area 6, so we'll type the area 6 parameter at the end of this network command. By doing so, we've configured OSPF correctly on router 1 in order for it to put its two serial interfaces into area 5 and area 6. Next, let's switch over to router 5 and configure OSPF on it. Just to make a point, when we get into config mode, we can type the router OSPF command and this time use a different process ID, for instance 5. Now that's not the area number, that's just a number, and it doesn't have to match between router 5 and router 1. So notice our command prompt changes, proving that we're in OSPF configuration mode. Now, both interfaces on router 5 are in area 5, so we'll use a much easier network command in this case. We'll say network and give an all zeros IP address and an all 255's wildcard mask. If you recall, that wildcard mask means I don't care what's in any of the octets, I'll assume all the octets match. Essentially, this network command will match all interfaces on router R5. Now, its interfaces are in area 5, so we'll type the area 5 parameter there at the end. And now we've fully configured OSPF with all interfaces in area 5 on router 5. Also note that if you look in your booklet, you'll see that R6's configuration uses a network command that uses the same address and wildcard mask configuration shown here on router 5. Now let's go to R1 and take a look at the routes learned in this case. If we do a show IP route command, we'll see a list of routes, all of which are either connected with a C in the left-hand column or OSPF learned with an O in the left-hand column. But notice there's nothing out to the right of this letter O. Now if we switch over to router 5 and do a show IP route command, we have both connected and OSPF learned routes here as well. But notice instead of empty space just to the right of the letter O, we have this set of letters that says IA. If we look up at the legend, you notice that IA stands for an OSPF inter-area route. If you examine R5's routing table closely, you'll notice that all the subnets listed there as OSPF learned routes happen to reside in a different area besides area 5. So from R5's perspective, those routes are inter-area routes. For example, subnet 172.22.10.0 is an inter-area route. That subnet sits between R1, R2, and R3 on a LAN, and it's in area 0. So R5 lists that as an inter-area route. Next, let's switch back to router R1. R1 is connected to area 0, area 5, and area 6. So as you see here in the output of the show IP route command, none of its OSPF learned routes have an IA in them. In other words, all the routes learned by R1 are intra-area routes because it's connected to all of the areas in this design. Next, let's move on to step 3. OSPF uses the concept of a router ID to uniquely identify each router. Each router uses a single 32-bit number written in dotted decimal format to identify itself when it's talking to other routers by sending OSPF routing updates. So when a router first boots up, it'll choose a router ID. Now there's a couple of ways it can choose its router ID. First of all, if the engineer has configured the OSPF router ID command as a subcommand underneath router OSPF, then that router has an explicitly configured router ID. However, if there's no router ID configured, the router needs a way to pick a default, if you will. So to do so, it uses the highest IP address of any loopback interface that's in an up and up state when OSPF comes up. Now that's a mouthful. Loopback interfaces are virtual or software interfaces inside a router. They can be assigned IP addresses just like any other interface. So a router will pick the highest IP address amongst all the up and up loopback interfaces as its router ID. However, if OSPF comes up on a router and there's no router ID configured and there are no up and up loopback interfaces, the router still has to have a way to pick a router ID. So it'll look for all its normal interfaces, look for those that are up, and pick the highest IP address amongst all those interfaces. To show some examples, we'll look at routers R1, R2, and R3 in this lab. None of these routers have the router ID configured, so they'll start at step 2, looking for loopback interfaces. R1 has 2 loopback interfaces, so it will immediately ignore the other interfaces. Looking at both of those, they're both up, and loopback 1 has the higher IP address of 11.11.11.11. So R1's OSPF router ID will indeed be 11.11.11.11. Now at router R2, we see 3 interfaces that are up and up. However, only one of those is a loopback interface. Because there's only one, R2 will choose that one loopback interface's IP address, 2.2.2.2, as its router ID. Moving on down to router 3, R3 doesn't have any loopback interfaces at all, nor does it have a router ID command. So it'll go to step 3 at its decision process, look at the regular interfaces that are up, and notice that 172.22.13.3 is the highest IP address amongst all those interfaces. Verifying the OSPF router ID chosen by a router is relatively simple. All you have to do is go to the command line interface and type in the show IP OSPF command. If you look at the first line of output, toward the end of the line you'll see the phrase ID followed by the router ID, which in this case on R1 is 11.11.11.11. We could repeat this process on each router to prove its router ID. However, R1 is adjacent or is a neighbor to all the other 4 routers in this particular topology. So there's another convenient way to find the OSPF router IDs as well. If you do the show IP OSPF neighbor command, you get a one-line entry for each neighboring router. Now the first column of this output lists the neighbor ID. Now if we know a bit about the topology and the IP addresses configured on those routers, we can easily discern which these neighbor IDs is indeed those routers' router IDs. For instance, we know from earlier diagrams that 2.2.2.2 is a loopback IP address on router R2, so that happens to be router R2's OSPF router ID. Now if we had forgotten that, we could look over to this address column on the right and notice address 172.22.10.2. That's the IP address of this other router on some connected subnet. For instance, in this case, that's router R2's LAN interface IP address on its FA0/1 interface. Continuing on down, we see router 3's OSPF router ID, once again shown a few minutes ago in the video. And then if you look at the IP addresses for the 3rd and 4th entries, we see 115.5, which is router 5's router ID, and 116.6, which is router 6's router ID. In this lab, you've seen how to configure the OSPF network command, and in particular how to use the wildcard mask to control which interfaces the OSPF network command matches. You've also seen how to configure an area border router by putting some interfaces on a single router into one area and other interfaces into a different area. You've seen how to distinguish between intra-area and inter-area OSPF routes based on whether there's an IA in the routing table entry. And finally, you've seen how an OSPF router picks its router ID.